All right, so today we're going to talk about determinants. We get in 3.1 and 3.2, and we've kind of defined determinant already. We've defined it for small systems, 2x2s, mostly because we needed it when we calculated the inverse. So we did the inverse of a determinant, inverse of a matrix. We said that equation is 1 over the determinant times some little manipulation of a 2x2 matrix. And so we defined it to be this thing. So we're going to use that to calculate these determinants. So notice the notation. Det A is the determinant of A, or we can write it as the matrix with these straight sides here. So I would write the determinant of 1, 2, 3, 2, notice the straight sides, would be 2 times 1 minus 2 times 3. Right, it's this product minus this product. So I have 2 minus 6, which is negative 4. Any questions about the first one? All right, the next one's going to be 4 minus 12, which is negative 8. And we have 6 minus 0, which is 6. And 12 minus 0, which is 12. All right, questions about those from the warm-ups? Any patterns to notice there? Anything you might question or want to? What were those last two? What's kind of an interesting thing to notice those last? Those matrices look kind of special. Hard to tell with a 2x2 really. But we do have a 0 in this bottom left-hand corner. That's all it takes to make one term 0. And so really the determinant of this one is just this product. I'm subtracting off nothing. So we'll just kind of file that away for later. All right, that's the warm-up. This is our plan for today. So take any questions you might have. Then we're going to talk about determinants, how we compute them for larger than a 2x2 matrix. Key properties of determinants are going to let us calculate them easier. A big laundry list of why we're actually going to use these things or where else you might see these. And lastly, some extra credit opportunity. Okay. So, before I get too far into questions, I'm going to start by going through that quiz that we returned real quick. So I'm just going to bring that up here. I'll talk through some of the solutions. So we're given the three matrices. The first one is going to be a value of 2, because I'm looking at the first row, third column. So that will be this value of 2. The dimensions of B times C, well, if B is a 3 by 2 matrix, and if this is a 2 by 2 matrix, the inside values tell me that I can multiply them because they're the same, and the result when I multiply them will be these outside numbers. Right, so when I'm done, it will be a 3 by 2. Of course, you can actually go through the process of calculating that product, and you would see the same result here. All right, the dimensions of D, if the dimensions of CD is 3, 5, so this one was kind of my fault. I actually meant this to have a value. Turns out there is no value here. Because if we have C, which is a 2 by 2, times something D, something by something, the result would have to be a 2 by something. It can't possibly be a 3 by 5. All right, so really you could have put doesn't exist, because really that is stated the question. But I decided that was a little bit mean on this one, so I'm just going to mark this one correct for everyone. I thought more about it. I thought, it is kind of a fair question because you should know that it doesn't exist, right? This, but the fact that I didn't really intend for that, so therefore I would have gotten it wrong, means I guess I'll mark it correct for all of you. So, okay, C inverse. Here we're doing our definition, so this is 1 over the determinant. The determinant in this case would be 1 times 0 minus 1 times negative 3. That's 1 minus a negative 3. Times the matrix where I flip the strong diagonal and I change the signs on the weak diagonal. So that would be a negative. And positive 3 here. I could leave it like that if I want, or I could actually multiply through the whole thing by a third. In which case I would get 0, 1, negative 1 third, and 1 third. That would be the inverse matrix. And all of these are worth 1 point on this thing. set of 4 vectors could be a basis for R3. That is false. If I have 4 vectors in R3, that cannot be linearly independent. They have to be linearly dependent. I know that a basis for R3 contains 3 vectors. That's the right number of vectors for a basis, and there is a perfect number. So if I have 4, one of them is extra. One of them must be a linear combination of the other ones. B, every subspace must contain the 0 vector. That is true. That's one of the 3 things we look for when we talk about a subset being a subspace. C is these 2 vectors are linearly independent. I can tell that quickly. If I have 2 vectors, for them to be linearly dependent, they would have to be multiples. These are not multiples. This is true. They are independent. All right, then we have this one. Is this vector in the null space? Well, the null space is the set of all x's such that ax equals 0. So if this vector is in the null space, then a times this vector should get me 0. I'll look at that multiplication real quick. First one I would get 0 plus 0 plus 0, but the second one I would get 0 plus 0 plus 1. So therefore it's not in the null space. So no. I wanted some sort of explanation there, but I didn't specify that, so I didn't mark it wrong, so I might have written y by your thing there, but I didn't take any points off for that. Find a basis for the null space. Well, the basis, once again, is finding all these solutions. So all I have to do is solve this thing. Now, I could take my matrix, if I wanted to, and augment it with 0, because that really will represent the whole system. But I don't really have to augment it with 0, because if I did, I had to do any kind of row manipulations, what's going to happen to my last column of zeros? Nothing, right? I'll add, subtract things, it'll still be 0. So, in some sense, I'm not going to write it just because I'm lazy, but I am going to know those zeros are there when I write my equations. Now, for this specific one, there's nothing to do here because it's already in row-reduced echelon form. So I can go right to my equations. This equation says x1 plus 2x2 equals 0. And the next one says x3 equals 0. That's right. x2 is my free variable, right? There's no pivot position in that column. So if I try to write out my solution, the set of all solutions to this thing, which will be some x1 value, some x2 value, and some x3 value. Well, x1 is equal to a negative 2x2. I could just take that first equation and solve it for x1 to get to that. x2 is my free variable, and x3 is equal to 0. So this is the same thing as x2 times negative 2, 1, 0. So what are my solutions for ax equals 0? Well, it would be negative 2, 1, 0, or negative 4, 2, 0, or negative 6, 3, 0. It's any multiple of this vector. Okay, so how do I build a solution space? I take a multiple of this thing. Right, it's the span of this vector would be all my solutions. So this is the basis for my solution space. So I build up my whole solution space. Any questions about that? Now, if there were 2 free variables, I would have x2 times a vector plus maybe x3 times another vector. That would be any linear combination of those 2 vectors. So that would be my basis, is those 2 vectors. Okay. All right. And the last one is, what is the dimension of the column space? Well, it's really easy and tempting to say 3, because the column space is the span of the columns. And I have 3 columns. So don't those 3 vectors form a basis for my column space? They don't. Why not?
They're largely.
Absolutely. So that means that there's, what's the problem then?
Need 2 vectors for a basis.
Absolutely. So basis has to span the space and be linearly independent. Right? Clearly they span the space because that's the definition, right? Is the span of these 3 vectors. So they're not linearly independent. We know that right away because, like you said, they're in R2 and there's 3 columns there. Also, we can see that this column is just 2 times this column. Right? So we don't just grab all the columns and call that a basis for the column space. We just grab the linearly independent columns. Those columns are marked by the pivot positions. So I'm just going to grab this one and this one, my 2 pivot columns. So if there's 2 elements in the basis, the dimension must be 2. The dimension of the column space here is 2. Okay, any questions from this quiz? Make sure if you have questions, you ask them. These will be examples of types of questions that will be on the exam. Any questions? All right. Any other questions from the homework or anything else? Thursday's class. Okay. All right, so now we're going to get into the determinant. What is the determinant? We're going to learn how to calculate it, so there's going to be a process of how we get this number that we're going to call the determinant of a matrix. But I think it's always useful to think about where this thing came from, because the formulas always seem so random. It's like, why in the world did some guy make up this crazy sum of weird stuff, negative ones all over the place? And where does this come from? Well, it was really designed for a reason. Most of our weird formulas are there to solve specific problems. So, the determinant was a tool to help us determine if there was a unique solution to a system. That's why they invented it or came up with it. So if we think about a small system, a 2x2 for instance, A, B, C, D. There is our nice little system. And I want to solve some equation where this is the matrix. I want to solve an AX equals B thing. Here's my A. Well, I can find the inverse if I want, but how do I know if there is an inverse? How do I know if there exists a unique solution? Well, one thing I could do is try to row reduce it to find that solution. If I start to row reduce this thing, well, put it in maybe row echelon form. I'd want to eliminate this position. So I'm going to take R2 minus, well, if I take this thing divided by A and times C, if I take A divided by A and times C, what do I get? C. So I'll take C minus C essentially. So that's the row operation I'm going to do. It's a little ugly because I have letters instead of numbers, but that's basically what I'm going to do. If I do that row operation, I'll get C minus C over A times A. That's the spot for my first row here. This simplifies to C minus C, which is 0, which is what I wanted. And for this position, I'll get D minus C over A times the row 1 position, which is B. This is what I'll get in this position. You say, wow, that's so exciting. You can feel the excitement out there. Woo. Okay, so it's like, what do we have now? Well, I have this thing in row echelon form now. So if I'm looking for when does there exist a unique solution always, it depends if this thing is 0 or not. Right? If this thing is 0, well then it depends on if there's a solution. Right? So if I have an augmented thing over here where it's 1, 2, if this is 0, there can't exist a solution. And if this is 0, I've infinitely many solutions. So there'll be a problem here. If this is not 0, then I could continue the process to get it in reduced row echelon form if I wanted. So the real question is this thing 0? So I say there does exist a unique solution when D minus CA over B is equal to 0. We'll take that whole thing and multiply by A to get AD minus BC equals 0. And that's the formula for our determinant. So really the idea is, let's calculate this piece and see if it's 0 or not. And what do we do in math lab? Well, we say, oh, great, now I know a way to tell if this thing has an inverse or not. I just do this. All right, then we want to tell somebody about it. Say, well, how do I know if this system has an inverse? Well, all you do is you make this one called A and this one called B, and right? You tell somebody else about it. You know, A's and B's. By the time you get the third person, say, oh, you just find the determinant. Like, what's the determinant? Oh, it's this thing. Right? You just give it a name, and everything kind of simplifies. And that's what they do. That's how this stuff is all generated. They go through some long process to get some formula, and they call this the determinant of A. All right, now we can simplify this stuff when we write it up and we talk about it. Okay? Any questions about that? Okay, so that's kind of the y. That lets us do 2 by 2s. What about bigger things? What about larger things? Well, we're going to have sort of a recursive definition. And that definition looks kind of ugly, so we'll go through it once using the definition, and then we'll break it down and do some calculations to make it not so tedious. And then we'll learn some properties to make them calculate much quicker. All right, so we have this crazy formula. The sum of -1 raised to the 1 plus j power times a bunch of stuff with little coefficients. All right, now this is only one definition for the determinant. There's actually lots of ways we can calculate it, but the process is all kind of the same. So we're going to call this a column expansion, because we're going to calculate the determinant using a column, using the first column, in fact. Sorry, let's see. Oh, it's the row expansion along the rows. So let's look at our first term in the sum. So we're basically going to calculate all this junk when j equals 1, and calculate all that junk when j equals 2, and keep adding those pieces up until we get to n, where n is the size of the matrix. So in our specific case here, we have a 3 by 3, so we're going to add it up from j equals 1 to j equals 3, from the first column to the third column. So if I start using the definition here, my first piece will be -1 to the 1 plus j. Well, we're starting off with j equals 1, so that's 1 plus 1 power, times a1, and once again, we're starting off with j equals 1, so this is a11. We're talking about a position in the matrix. That's this position right here. Then times this thing. This is a subdeterminant. It's the determinant of the matrix you get when you eliminate the first row and the jth column. So this case we're working on j equals 1. So we're going to eliminate the first row, eliminate the first column, and we get a little submatrix in here. A little 2 by 2 that's left over. This little 2 by 2 right in here, which is 1, 0, -1, 0, times that determinant. So that's me evaluating that expression when j equals 1. Then I say plus all that stuff when j equals 2. -1 to the 1 plus 2 power. This is going to be the a12. That's just this position now. I'm just going over. This value is 2. Now once again I have a little subdeterminant. The subdeterminant is eliminating the first row, and now it's eliminating the second column. I have 4 values left over now. I have these 4 values. I take the determinant of this little submatrix. So 1, 0, 2, 0. 1, 0, 2, 0. Plus all that stuff again. 1 plus 3 here. Now I'm looking at the a13 term. That's this term. And another subdeterminant. Now I'm eliminating the first row and the third column. So I have 1, 1, 2, -1. All right, any questions so far? All right, that's the ugly piece. Let's use this formula and plug in the i's and the j's. Well, what are we really doing? We're just expanding along this first row. This is a row expansion. I take the first term times this little subdeterminant, plus the second term times the subdeterminant, plus the third term times the subdeterminant. The only other thing we have to add in here is this weird -1 raised to a power. Right, but it's raised to the 1 plus j power. So all it's going to do is switch signs, because if we see here, well, we have -1 squared, that's going to be +1. And we have -1 cubed, well, that's going to be -1. -1 to the 4th, that's going to be +1. So all this is doing is alternating the signs here. So really, it's like we can just say positive, negative, positive. I kind of think of those having those values. So all we do is take this value times little subdeterminant, minus this value times subdeterminant, plus value subdeterminant. And that's really the process you go through when you do this expansion. And it's just going to be easier to think about it that way instead of doing this the sum of some stuff. Questions about that? So in this case, we're going to clean this up. This is just positive 1. I have a 1 here. And now I have a 2 by 2. Well, great. I have a formula for a 2 by 2. So I determine it's going to be 0 minus 0. I get a big old 0 here. Now I have minus, because this is going to be a minus 1, times 2, times this subdeterminant. What's that determinant going to be? 0. So this is also 0. Plus, because I have negative 1 to the 4th, 3 times this subdeterminant. Negative 1 minus 2. So that's negative 3. So altogether, 0 plus 0 minus 9 is negative 9. And that's our determinant. Like given this matrix, this is the determinant value. Any questions about that? That looks like a pain in the butt, right? Okay. A couple things here. One, we need to know how to do this. This is a 3 by 3. Well, what about a 4 by 4? Well, you do the same thing. The only difference is if it was a 4 by 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I would do the same thing. I would take this number, I'd go plus, minus this number times the subdeterminant. But now my subdeterminant is a 3 by 3. Oh, crap. All right, now I have to write up that thing, and for each one of those 3 by 3s have to go through the same process to get those down to 2 by 2s, or actually have the formula. Okay? So imagine doing a 10 by 10. Right?
Okay.
Not fun, but there's going to be a lot of shortcuts, right? So that's what we need to figure out here as well. We always need to start with the definition. So this is the definition. Now, one shortcut we can use right away is just generalizing our formula. There's actually a process to go through this. And the question is, why did we pick the first row? Turns out we don't have to. Turns out we can expand along any row or any column. Okay? And really the only thing we have to adjust in our formula is if, well, we want to expand along a different row, we just change these values to 2 and 2. 2 up there. And if we want to expand on a column, we just flip the variable. All right, that's really it. The only thing we have to kind of keep track of is this negative 1 thing. And it turns out that when we start, we can actually just go through and assign that value to each of these. We just start and alternate the signs here. Positive, negative, positive, negative, positive, negative, positive, negative. That really assigns that sign value to each of the positions. And now we can say, go ahead, expand out any row or column. Now, why is it useful to expand out any row or column? Well, if I had to pick a column to expand along, I'm going to pick column 3. Because I got a bunch of zeros there. Because that's going to look like if I expand on this column, I'll grab this value, 3, positive 3, times a subdeterminant. Well, I eliminate the first row, first column. I get 1, 1, 2, negative 1. Then I go minus 0 times subdeterminant, don't care, right? It's 0. Plus 0 times subdeterminant, don't care, because it's 0. So all I have to do is that one calculation. So choosing the right row and column can be very useful. Once again, if I do this, I'll get 3 times the subdeterminant, which is negative 1 minus 2. So of course I get back to the same value I did before. Okay? All right, questions about that? All right, so that's the first shortcut trick, is choose your row or column carefully. Your turn. Here's 3. Okay, and just real quick so we can kind of check our work when we're done also. The mathematical command is just DET, just like the mathematical notation, where it's capital letter and brackets. So I can calculate the determinant of the matrices. I can encourage you to do the most is actually to write out the steps. Don't try to calculate everything at once. Write out those numbers and just write out that subdeterminant inside of the notation. Track it. As I get started, which column should I expand through for the first one? Or row? Third column. All right, so I got plus, minus, plus, minus. Let's see, and we have to be careful here. Should this be a plus or a minus? It should be a minus. Why is that? Remember, all these come from -1 raised to the position value, basically. So this is the 2, 1 position. 2 plus 1 is 3. -1 to the third is -1. So we can kind of double check our signs as we go. All right, now I'm going to expand on that third row. I'll get 0 times some submatrix plus 0, or minus 0 times some submatrix plus 2 times some subdeterminant, where I eliminate that row and column that value is in. I'm going to get 0, 1, 2, 0, 1, 1, 1, 2, 1 is my subdeterminant. It would be that stuff minus 0 times some other determinant. So I've simplified quite a bit just by using that correct column. Now I got to keep going here. 2 times. Now let's calculate that determinant. Well, I'm doing that determinant, which row or column do I want to expand along? First column. All right. I'll have 0 times some submatrix, so I have plus, minus, plus, minus, plus, minus, plus, minus, plus. So 0 times some matrix minus 0 times some subdeterminant plus 1 times some subdeterminant, where I eliminate the first column, last row. Now this little subdeterminant is 1, 2, 1, 1. Those go away. Now I have 2 times 1 is 2 times this determinant. 2 times 1 minus 2. Negative 2. And we could confirm that with Mathematica there as well. All right, questions about that calculation? Okay, we're not going to do a ton of these in class. In general, I want you guys to exercise a lot of these and do the problems so that you know you're comfortable with it. It's one thing to watch me go through this and say, yep, that looks right. It's another thing for you guys to go through the steps. Now, this is one of those things that you can really test to see how well you're doing. Right? Generate pretty much any random matrix in Mathematica and find its determinant. And calculate determinant of matrix, right? So you can give yourself infinitely many practice problems to do this. Right, so that's what I really encourage you. Same thing like matrix multiplication, those other mechanical operations. Those are the ones that we're not going to spend a ton of time in the class, and you just got to go home and pound them out, right, as many as you can do. Now we got to do the next one, a transpose. Well, before we dive too much into this, let's just think about the process. If I had to pick a row or a column, which one would I expand along? Row 3. Row 3 looks a lot like column 3, right? Just the transpose. I just flipped my rows and columns. So if I expand along this direction, it's going to be 2 times some subdeterminant. Well, if I eliminate that row, that column, I get 0, 0, 1, 1, 1, 2, and 2, 1, 1. Which looks like the transpose of this little piece. If I want to expand along this one, which one do I expand along? Row 1, which looks like the column 1 of before. All right, so this is going to be 2 times 0 plus 0 plus 1 times some subdeterminant, which is 1, 1, 2, 1, which looks just like the transpose of this piece. And if I calculate that piece, I will get 2 times 1 minus 2. Because when I take the transpose there, by switching the terms, if I look at this 2 by 2, all the transpose does is flip these. And so all it does is flip the order of the product when I take that last determinant. It doesn't change the value at all. So what does this tell us about the relationship between this and this? It would be the same. So in general, I take some random, be nice, I'll say integer value. Random integer between 1 and 20. And let's take a 4 by 4 matrix of those things. There's a random matrix generated by Mathematica. I'm going to call that A. If I find the determinant of A, I want to find the determinant of A transpose, should be the same value. Okay. All right, questions about that? All right, so that's the first property that's going to be useful. If I have to calculate the determinant of a transpose, the same thing as the determinant of the original matrix. The next one, let's think about this expansion. Now, I could expand on the first column or third row. I'm going to do the first column here. All right, I'm going to take 2 times some subdeterminant. That subdeterminant is going to be 1, 4, 0, 2. But I did a couple of those in the warm-up. And that little subdeterminant, well, it's just going to be this product, the 1 and the 2. So really, this is just going to be 2 times 1 times 2. This times this times this. Now what if I had a bigger matrix? 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 8, 9, 0, 0, 0, 10. If I wanted to calculate that determinant, it would be 1 times a subdeterminant. 5, 6, 7, 0, 8, 9, 0, 0, 10. But I just did a 3 by 3 that had zeros below the diagonal. And it turned out the determinant was just this product. So it tells me if this thing is triangular, in other words, I have a diagonal and numbers just on one side of it, this is upper triangular, then the determinant is just going to be the product of the diagonal elements. Because this thing is triangular, every little subdeterminant is triangular as I go down the blocks. Okay. All right, so that's a quick justification of that, but that's an important simplification. All right, now if we have a triangular matrix, it's really easy to calculate a determinant. All we do is take the product of the diagonals. All right, so now I got a list of properties that we're going to go through. We've hit a couple already. So let's generate our master list here. All right, if A is triangular, then the determinant of A is the product of the diagonal entries. That's the one we kind of just explored. Okay, so we've talked about the first one. If we have a triangular matrix, all we have to do is take the diagonal elements. We've talked about the second one. The determinant of A transpose is the same thing as the determinant of A. And then the third, fourth, and fifth are all kind of related. They all really come one after the other. I would say this is the most important one. The determinant of the product of two matrices. And before I even say this, we should stress back at the beginning, we define the determinant for square matrices. These are for n by n's, not m by n's. Right? So they're all square. So we have a square matrix A, a square matrix B, which tells us we can multiply them, and the product will also be n by n. If that's the case, then the determinant of the product is the product of the determinants. That's the thing you would chant, right? We all gathered in a circle and we say, the determinant of A, B is the determinant of the product is the product of the determinants. Okay. And the last one, if A is invertible, first of all, it's invertible if and only if the determinant is not equal to 0. That's an important one. That's kind of the idea that generated the idea of the determinant. But also, then the determinant of the inverse is equal to 1 over the determinant of A. And we see that last one, we should say, wait a second. 1 over A, can I divide by a matrix? Did we have a big talk about that? But that's not the problem here, right? Because this isn't dividing by A. This is dividing by the determinant of A. Because the determinant is just a number. It's kind of a neat thing of what this determinant is doing. It's taking some thing that lives in a space called Rn by n. Right? It's a matrix. It's a weird list of values. Right? It's not R2 or R3. It's like 2 by 3. It's a list of rows and columns. But it's taking that information and mapping it all to just R. It's giving a number value to a matrix. All right, so let's talk about a couple of these here. All right, so I'm going to talk about 4 first. 4 is the one that we're going to take as our starting point. We're going to believe that one. The proof is a little bit long, so we're just going to have to trust that one's true. Now, of course, we could test it a bunch of times. We saw it's generating a random matrix in Mathematica. I could generate a couple and just kind of keep testing that to my heart's desire. That's not a proof, of course. After a couple of those, I'd feel pretty confident, right? So that's the one I'm going to take to be true. The determinant of the product is the product of the determinants. Now, once I have that, I can look at the next one. If A is invertible, so if I have this matrix inverse, Now we kind of know that it's only invertible if the determinant is not equal to 0. Well, we established that's why they created the idea of the determinant. So now if I look at a product, A inverse times A, what do I get when I take that product? What is A inverse times A? Identity, absolutely. That's the definition of the inverse. Now what I can do is take the determinant of both sides. Right? If those matrices are equivalent, right, then their determinant should be the same. But on the left-hand side, I have the determinant of the product. Well, the determinant of a product is the product of the determinant, so this is the same thing as the determinant of A inverse times the determinant of A. But now these things are just numbers. They are just real numbers that I've assigned to these matrices. So if I want to solve for the determinant of A inverse, all I do is divide by, oops, this is the determinant over here, the determinant of A. And up here I don't have to write the determinant of identity anymore, because what is the determinant of identity? 1. Right? Because that's just a whole bunch of 1s on the diagonals and 0s everywhere else. Certainly triangular. So that's where that comes from. It comes from a real quick application of that product rule here. And of course we can test it here. I already got a matrix loaded. Determinant of A was this thing. What's the determinant of A? Inverse of A. There you go. Okay. All right, and the last one is the determinant of A is n linear. What does that mean? That means if I think about a transformation and I fix all the columns but one, it satisfies the properties of a linear transformation. And our properties of a linear transformation were this and this. Preserves addition and multiplication. So your book goes through that a little bit. I'm not going to stress it here and go through the proof of it here. I'm going to focus on the other ones. So the one we have left to cover here is 3, the determinant of row operations. And this is an important one because that determinant calculation was challenging. It's much easier to take that 4x4 and row reduce it than it would be to calculate that ugly determinant thing with all the little subdeterminants. So the question is, can we row reduce it? That would make things a lot easier if I could just row reduce it and calculate that determinant. Turns out we can, but we have to be a little bit careful. Row operations do change the value of the determinants, but they change them in very predictable ways. So we got the ways here. If I add multiples of rows, that doesn't change the determinant at all. If I switch rows, I do a row switch, it will change the sign of the determinant. And if I multiply a row by some number, then it will change the, if I just multiply a row by b, then I need to multiply the determinant by b. Multiply the determinant by b. So we can memorize those, or we can think about why they make sense. All right, so here's my determinant A, or here's my matrix A, and I want to find the determinant of this thing. So what I'm going to do is I'm going to go through a row reduction. If I want to row reduce this thing, what's the first step I would do? Actually, take a second on paper real quick and row reduce this matrix. Move around here. Shake the arms to make everything nice. Do a quick row reduction of this thing. My battery just died. Really what I need is a list of your steps as you go. So as you're doing the row reduction, think of the steps you're using. All right, what was the first step in your row reduction? It was row 3 minus row 1, is that what you said?
Sure.
Okay. Now, you can do the augmented matrix and do the row reduction, but we talked about, when we talked about inverses, that every row operation can be done with an associated matrix multiplication. I really encourage you to take a look at that extra credit because it's really not too bad if you take a little look at it. But basically, if I want to do that operation, I can just take my matrix and multiply it by some other matrix, an elementary matrix, where essentially all I do is that row operation to the identity matrix. So if I started with identity and I wanted to take R3 minus R1, I would just get a negative 1 there. If I multiply those two matrices together, it will look like this matrix with R3 minus R1. It will do that operation for me. That does the row operation. Okay. Now what was the next row operation you did? I didn't do them, so you got to help me. What was the next row operation? It was, what was it?
R1 adds up.
So if I did this first one, I would get 0, 1, 3, R3 would be 0, minus 2, and minus 1. This thing. What will be the next operation here?
R3 plus 2R2.
R3 plus 2R2. So, to do that one, I'm going to do the same thing to identity. R3 plus 2R2 would be a 2 here. That matrix should do the same operation. And if I actually did that row operation here, I would get 0, 1, 3, 0, this plus 2 of that, 5. Good, like that. So what that means is if I do this product, I should get to this thing. Okay. So instead of doing the row operations, I'm just doing it with matrix multiplication, but I know I can do that. Now the reason that's useful is because I can take the determinant of both sides. Determinant. I'm essentially saying that the matrix I started with is this thing. Right, and then I have this matrix I'm getting to in the end. This is the matrix I started with here. This is my A. I'm multiplying by an E1 or an E2 into getting to this nice thing over here. And the determinant should be the same. Well, the determinant on the left side is the product of three things, so it's the determinant of 1, 2, and 3. What's the determinant of this one? Just 1, right? It's a triangular matrix, so I can just take the product of the diagonals. What's the determinant of this one? Sorry, it's not I, it's 1. 1 and 1. And then over here, I just have my determinant of A. On the other side, I have the determinant of this thing, which is also diagonal. So this is just going to be 5. Okay. So if I was going through these steps and thinking about the row reduction, I would have had to add a multiple to this row, but that doesn't change the determinant. Because essentially it's the same thing as multiplying by this matrix. Right, so the determinant of this thing is equal to the determinant of this product, but that row operation doesn't change the determinant here. Because the determinant of this thing is just 1. Now if I had to take a row and multiply it by something, like I wanted to take this thing and make this a 1, I would divide it by 5, in which case that would change the value of the determinant. Right? If I multiply a row by a factor like 1/5, it will change the value of the determinant by 1/5. Right? So as this process of going through the row reduction and calculating our steps, it can help us kind of gather up the values here. So basically, I'm row reducing to some nice diagonal form, and along the way, I'm keeping track of the factors I'm changing it by. Any questions about that? Okay. Now, when we look at this little process here, this is a very important process that we go through. It's called LU decomposition. It's something we skipped in chapter 2. It's in section 2.5. So I'm just going to point it out real quick and offer it up as an extra credit assignment if you want to play with it. It's called LU factorization. If I take a matrix A, I should be able to factor it into the product of two other matrices, L times U, where L is a lower triangular matrix and U is an upper triangular matrix. Right, so I'm basically taking an A like this and breaking it into something with numbers down here and zeros up here, times something with zeros up here and numbers down there. Oops, flip that. Zeros there, numbers here. And a lower and an upper. Now how do we do that? We basically just do exactly what we did. When I row reduced, I gathered up these E's, and if I take this product, all I'm going to get is a lower triangular matrix. And so then if I just take the inverse, which I know I can do because these are elementary, I'll have lower times upper, that should equal A. So that's the process of the decomposition. And we really use this decomposition because that's how your computer or your calculator does determinants. It does an LU factorization, and then it will find the determinant of the product. So in other words, it will first decompose it into this, and then to find A, it will just do this. Okay? That decomposition is like pre-processing our matrix. So this matrix is hard to work with. So instead, I'm going to break it into a form that's easier to work with. It's L and U. And we'll do a lot of other operations on L and U as opposed to A. For instance, if we wanted to solve a system that looked like this, AX equals B, for a whole bunch of B's, so AX equals B1, B2, B3, B4, we talked about finding the inverse because now we can just apply it to all our different B's. That's a good thing to do. But in fact, in application, this is a better thing to do because we can use the decomposition to solve those systems just as fast as the inverse, and it turns out this is more accurate because there's some errors that come up, rounding errors, when we generate the inverse matrix. So the LU factorization is a real useful thing in application. We don't really have time to cover it, so I won't test you on it. But I'm going to post an extra credit assignment based on it. It's going to have you basically form it like we did for the other extra credit. So you'll come up with a couple E's, you'll show the LU decomposition, and then you have Mathematica calculate it to kind of verify it. All right, that is all I got for today. We pretty much got all through 3.2. So what we're going to do is we're going to work a little bit ahead and give a little cushion for Thursday to have kind of a review session, maybe a worksheet here where we call really solidify these ideas. So that means for tomorrow, we're going to start on 5.1. So I answer any questions you have on 3.1 or 3.2, and then we're going to start right away on 5.1. All right.
Review session on Thursday. Does that mean we have something coming up next week?
Not next Monday. I think the exam is the
Thursday.
Thursday?
And the finals Friday, the next week.